Hi everyone, my name is Nick. I'm going to be your host this evening for our project here, Coupled Oscillator Baddies. Throughout this lecture slash information session, we're going to be talking about linear algebra's implementations on physics, specifically coupled oscillators, which is an amazing example to see how it really applies to simplifying systems and helping us to solve very complicated ideas. First off, we're going to start with Stella, who's going to cover a general topic of the physics that's going to be covered in this video, in addition to the math, such as ordinary differential equations.
Hi class, my name is Stella, and today you are all going to become experts in how to solve a system that deals with coupled oscillators. But first, let's talk physics. You might already know that mechanical problems in physics are all governed by forces. From just knowing the forces that act on an object, you can determine many important things about the motion of that system. This is exactly what we're going to do today with this horizontal spring mass setup. As you can see here, we have 3 springs, all with the same K value, and 2 masses, all with the same mass. A spring's K value is essentially a proportionality constant that measures a spring's stiffness. And don't worry about it for now, but we're going to come back to it later a little bit in the problem. But first, let's go back to force real quick. You're likely familiar with Newton's second law. F equals ma. Force equals mass times acceleration. Using this one equation, we can derive an expression for the motion of an object, specifically one of the masses in the system. Let's focus on just this one simple spring and mass right now. Springs are unique in that the force that a spring exerts can be described by Hooke's law. Hooke's law says that the force you need to stretch or compress a string is F equals negative kx, where F is that force, of course, K is that K value I was talking about earlier, and X is just the displacement of the spring, typically from a equilibrium point where the string isn't stretched or compressed at all. But anyways, from Hooke's law, we can derive this equation of motion that we want. Like I said, F equals ma, and for a spring, F equals negative kx. For this system, let me quickly draw a free body diagram, aka the forces acting on the mass. So, we have F equals ma, negative kx equals ma, and finally, if we write the acceleration as a second time derivative of position, this is just the notation I'm using, those 2 dots mean a time derivative in the second one, we have a differential equation that we can start working with. X double dot equals k divided by mx. And in this equation, x just describes the mass displacement along the horizontal axis. So that is the displacement of this mass. And keeping these x's all in order with subscripts saying 1, 2, 3 will be very handy when we're dealing with more than one mass. So now we have a differential equation, and solving this is going to be a whole problem in itself, but we're in linear algebra, so I'm just going to say, who cares, and give you guys the solution to this differential equation. The details on how I got to this solution aren't important, but if you're curious or if you've heard of it, this is just the solution to a well-known simple harmonic oscillator, like a pendulum. So we have this differential equation, and we have the solution for the differential equation, and what you can see is I have an x and an x double dot. So what I can do is I can take the derivative of that solution, x, take it twice to get x double dot, and then plug that in. Here are the derivatives right here. And as you can see, when I plug it in, the cosines on both sides are going to cancel out, and what we're left with is a for where x was, and negative w squared a for where x double dot is. All right, this all may seem like it has nothing to do with linear algebra, but I promise soon that will all become clear. But what I just showed you was how you can use Newton's second law and common differential equation solving techniques to focus on the motion of one spring and one mass. What you are all going to do is do it with a much more complex system. For masses that are coupled, you're going to see their individual displacements appearing in each other's differential equations of motion. Hence the name coupled. They show up in each other's equations. All you have to do when you have a more complex ODE is take these different solutions and assign different coefficients for each mass that you're observing. So to make that more clear, say if you had 3 masses, each with their motion x1, x2, and x3, that's what I was saying earlier about the subscripts. Just change each solution so there's a different coefficient that corresponds to the variables. So for example, here I have x1 equals a cosine wt, x2 equals b cosine wt, and x3 equals c cosine wt. This will all come in handy in a few minutes, but I think you guys are all ready to solve coupled oscillators using the eigenvalue equation and matrices. Good luck!
Next up, we have Nina and Andrea, who are going to work through an example problem of a working coupled oscillator, and therefore we can actually see how the linear algebra we're learning is applied to this physics and helps even out and kind of simplify this math.
This first example problem will help us understand how to write these coupled oscillator equations in matrix form. If you remember from class, we learned of matrix equations in the form AX equals B, where X and B are column vectors and A is simply a matrix. Here, the process is extremely similar. We want a matrix equation in the form AX equals X double dot. So first, we need to distribute out the terms so we can write it in matrix notation. Here, Andrea is just distributing it out so we can figure out what our coefficients are and what our x1 double dot is equal to. Again, she's repeating the process to figure out what our x2 double dot is. Now that we have our equations, we can write it in matrix notation. So we're going to have one column vector that's going to be the x1 double dot and the x2 double dot, and we're going to make it equal to our matrix of coefficients, which is going to be our A. And we simply just took out the k over m because it's present in all of those coefficients. And lastly, we're going to have another vector, which is our x, with x1 and x2. For the second example problem, we're already starting off with our equations in matrix notation and simply finding the eigenvalues. We're doing the same procedure as we did in class by taking the determinant as seen and just setting it equal to 0. So after writing out the determinant, we set it equal to 0 and start distributing out terms. And here we're going to get some sort of quadratic equation in which we're going to factor it out and get two values, so lambda 1 and lambda 2. In this case, we get lambda 1 as 5 and lambda 2 as 2, since lambda minus 2 equals 0 is 2 and lambda minus 5 equals 0 is 5. We have to remember to add in the k over m because our original matrix is actually multiplied by k over m, so it's really important to add that at the end. Now, physically, this next part can be proven, but what's important to know here, math-wise, is that lambda is equal to omega squared, which is our frequency. Now, we write it out again, and we're going to get some sort of square root k over m, and again, some square root k over m, and these are the solutions to our normal modes.
Welcome back, guys. Hope you're hungry for some more coupled oscillators. Next up, we have Jacob, Tripp, and Fabrizio with an actual demo of a coupled oscillator, which should be pretty fun to see.
Alright, welcome to the cool part. We're here in the Mechie lab with a physical representation of your coupled oscillators. So here we've just got two pendulums attached by a string, and we're just going to show the two different normal modes that the system has. So the first normal mode is just when they're swinging in phase with each other, which means that they're swinging at the same speed, same relative positions to each other. So if you want to show that, Tripp.
My angle gives us a little more accuracy.
So as you can see, they're pretty much moving in the same phase. Like, they start to get a little more out of phase just because it's an imperfect system, but in a perfect world, it'd be the same. The second phase is when they're swinging perfectly out of phase. So we'll set them up pull the opposite of each other.
All right, it's the second half. You are my second half.
3, 2, 1, go.
Hopefully this physical demonstration helped in clarifying and make more sense of all the math that you saw in the past couple of minutes.
Normal modes are essentially just angular frequencies, and in these cases with coupled oscillators, it refers to the patterns of the different masses and how they move in a sinusoidal way. So when we find out what our normal mode is, we're finding out what the angular frequency, aka angular velocity, is of each mass. Okay, so in this example, where we have these two masses on a spring setup that can move in this singular plane, we're going to have two normal modes of the system. Case one is where M1 is pulled to the right and M2 is also pulled to the right. So once these masses are moving and they're oscillating back and forth, they're going to have the same angular frequency. So the normal mode, W1 is going to equal W2. That's our first normal mode. Case 2 is when initially if we pull these two masses apart, we pull mass 1 to the left and we pull mass 2 to the right. These two are going to oscillate with the exact opposite angular frequency. So that second normal mode is going to be, for example, negative W1 equals W2, indicating that they're at the same angular velocity except completely in opposite directions. More formally speaking, they are exactly out of phase with one another. So that's what a normal mode is, and it's exactly what you saw in the demo when Fabrizio, Tripp, and Jacob showed how you can move the coupled pendulums in two distinct different ways. With the pendulums and with the springs, it's the same situation with these two different normal modes. So now I think you're ready to solve some problems.
Now we have reached the ending segment of our video for coupled oscillator baddies. Hopefully you've had an amazing time watching our videos. We've had a great time showing you all the different aspects, from the general background for physics and ordinary differential equations for coupled oscillators to an actual live demo, which my teammates made, which I thought was pretty cool. And we even did an example problem, which will be helpful for our homework, whether or not you guys actually do that. I think this is really cool because some of the things here that really make this important is we can see how we can use linear algebra to take ordinary differential equations, which are very complex equations, and simplify them down into individual numbers where we can solve for specific values. And I think that's the kind of the beauty of linear algebra, is we're able to take complex systems and isolate them down basically to a puzzle and then solve for individual aspects. And we can see here its application in the real world, which is actually amazing. Like, it's crazy how much you can do with math. It's been a pleasure to be your guys' host this evening. I hope you guys had a great time, and hopefully our video wasn't too long. Thank you.
Want to get my second half?
Yeah.
Oh, you are my second half. I can't. I'm sorry. I think that's what it is. Alright, let's keep the first one.
Breathe.
Stop. Okay.
Breathe, okay.
Stop.